Unit 7, Lesson 4, and the last learning objective. Today, in this part of the lesson, we're going to learn why we even learn about logs. What is the purpose? When you see a problem in which we're solving for x in examples A and B, we can use mental math. 10 raised to what power equals 100, x equals 2, no problem. 2 raised to what power equals 32, x equals 5, no problem. This means 2 to the 5th, 2 times itself 5 times is 32, and 10 times itself twice equals 100. But not all problems are going to be that simple. What if we have something like this? 10 raised to what equals 13? Well, I know that 10 raised to the first is 10, and 10 raised to the second is 100. So if you're a visual learner like myself, then we know the answer for x lies between 1 and 2, but how can we get an exact answer like they're looking for? That's why we have logs. Logs are used to solve when the variable is in the exponent position and we can't use mental math to solve it. So how do we use logs? Well, we use logs by doing the following. So this is the problem, and I'm going to provide us a little more space here. We take whatever this is, and I write in front of it log base 10. And over here, the exact same thing to keep the equation balanced. Whatever base we're trying to remove to solve for the variable is what I write down below. Now, if you recall, we talked yesterday about how we could say like log base e of e was 1, and log base 2 of 2 was 1, and log base 10 of 10 is 1, right? When this value, the base, is exactly the same as the number behind it, it will always equal 1. We'll look over here. It equals 1. Well, what do we do with the x? This variable position just drops down in front at the same level. So it's like x times 1. 1 times x is simply x. Now x equals log base 10 of 13. This is considered to be the exact answer. Now, when you're asked to give both the exact and the appropriate answer, approximate, it should have been not appropriate, should have been approximate answer. The approximate answer can be achieved on the calculator by hitting the math button. And remember, you have that online calculator when you go to our Google Map page. And then you're going to use the arrow to go up 3 times until you hit log base. So the base here is 10, and behind it is 13. And now I'm going to approximate to the thousandths place, so 1.114. Let's go on to part D. When you can't use mental math to solve for a variable that's in the exponent position, we rely on logs. So I'm going to rewrite this, giving myself a little more space. And now what I drop in front of both, because we have to keep the equation balanced on the left and right, is I look at what is the base I'm trying to remove so I can solve for the variable in the exponent position, and then write log base e on both the left and right. I also want you to recognize that log base e is equivalent to ln. Now we just talked up here how these are exactly the same, the base and the value behind it. So this becomes a 1. What's in the exponent position drops in front. So it's like 2x times 1 equals log base e of 15. Well, 2x times 1 is just 2x equals log base e of 15. Isolating for x, we're going to divide by 2. So the exact answer could be written as log base e, or maybe you prefer ln. I'm going to put parentheses around it because that's one portion, and then we'll divide that entire portion by 2. I don't want students to think that 2 should only be divided by the 15th, divided by this quantity. That's the exact answer. Now, we do have a button on our calculator that is ln. You can see it right here. So I can do ln of 15, get an answer, and then divide it by 2. So x is approximately 1.354. Let's take a look right now at our example here with e. So I can't do mental math. I don't know what I can raise 4 to the power of, and then divide by 13, and I end up with 3. I just don't know. So what I'm going to do is first get this by itself. So I'm going to multiply both the left and the right by 13, because opposite of divided by 13 is multiplying. I know 3 times 13 is 39. Okay, next up. Now, I'm just going to do an approximation in my head, just so I can see this. 4 to the first is 4. 4 squared is 16. 4 to the third, so 4 times 4 is 64. Now, look at this. I need 4 to what power equals 39? 39 is like in between 16 and 64, so I know my decimal answer will be between 2 and 3 if I'm making a prediction. But how do I actually go about getting an exact answer here? Well, I need to remove the 4 so that I can solve for x. So both to the left and right, I do log base 4. Remember that this will equal 1, and the exponent comes down below. So x times 1 equals log base 4 of 39. We know x times 1 is just x. So here is the exact answer. Now, how do I get the decimal answer? It's not an ln, so I'm going to go to math. I'm going to hit the arrow up 3 times. Whoops, my calculator is a little slow there. I have a base 4. The number behind is a 39. And here we have it. So x is approximately 2.643 rounded to the nearest thousandths. Well, let's look at example F. So PEMDAS, please excuse my dear Aunt Sally. I want to get this portion by itself. So adding or subtracting the side that contains it, I'm going to subtract 8 from both the left and the right. Notice that the x plus 8 is not in parentheses, and this subtracts to equal 5. Now, how do I remove a multiply by negative 3? I'm going to divide by negative 3. And whether that negative sign goes in the top, in the bottom, or the middle, doesn't really matter. Now this confuses students. They're like, what are we supposed to do? So this is log base e of x equals negative 5/3. Now this looks different than our previous answer. So we're trying to now solve for a variable that is no longer in an exponent position. So you're going to learn a new skill with this. We're going to take whatever this exponent is that allows me to remove the log. We're going to take whatever this base is that would allow me to remove the log. In this case, it's e. And I'm going to make this the base, and this is the exponent. And we need to do that to the left and to the right. So base exponent, base exponent. Now, what does that do? This portion is going to reduce down to, or simplify to 1. So if I ever said 2 raised to the log base 2, it simplifies to 1. 3 raised to the log base 3, it simplifies to 1. And whatever is directly behind it, in this case the x, just becomes x times 1. Or here, x times 1. The same thing here. This simplifies to 1, and the x comes down in front. So I have x times 1 on the left-hand side, which is known as x, and that is equal to e raised to the negative 5/3. This is your exact answer. Now, how do we find the approximate answer? Well, e here is in blue, so I need to hit the blue key in e, and then raise to the negative 5/3. We have x is approximately 0.189 when rounded to the nearest thousandths. Okay, let's look at g here. We want to get this portion by itself, so PEMDAS, please excuse my dear Aunt Sally. I'm going to start by adding or subtracting. So I'm going to subtract 6 from the left and 6 from the right. Negative 2 times this quantity, the natural log of 3x minus 1 equals negative 2. Then I'm doing multiplying or dividing. We have the natural log of 3x minus 1 equals positive 2. Oh goodness, what do we do here? Well, remember, natural log is the same as log base e. And I'm back to a problem that was similar to the last example in F. I'm trying to solve in a situation I can't do the mental math, and I'm trying to solve here for this variable. Let's write this in exponential form. E raised to the second equals 3x minus 1. How do I solve for x? I'm going to add 1 to both sides. E to the second plus 1 equals 3x, and then I'm going to divide by 3. So I think the exact answer is this. So I'm going to go e to the second, bring it down, plus 1. I really should have it all in parentheses. So e squared, and then divided by 3. And the approximate answer is 2.796. And again, plugging this in and subtracting by 1 every time. You have to check if I've been forgetting to do that. Every time you've got to plug it back in to make sure that this value behind the log base is positive.